So now we'll discuss about switching transient in the transformers. So we know that in a transformer the voltage and the flux, right? If Im is in this direction and flux is in this direction, then we know that the supply voltage or applied voltage is actually leading the flux by an angle of 90 degree, right? Which we have seen in the phasor diagram in the initial lectures, right? So if this is the, let's say this is the voltage waveform, the black one is the voltage waveform and this is the flux wave. So what is the switching transient is like when we are actually connecting my transformer to the supply voltage. That instant actually decides like where on this point we are actually turning on this switch. Okay, that actually decides the severity of this switching transient. Let's see how. So let's say we are turning on this switch SW at a moment when this flux is exactly 90 degree with this time instances, let's say. Okay, let's say Vm or Vt, if I'm saying that this is Vm sine omega t and plus let's say theta. Theta is the angle at the time instances when I am turning on this switch. Okay, that theta would be decided by the time instances when I am turning on this switch SW. Okay, so let's say I am turning on when this theta is at 90 degree. So obviously at that time the flux would be 0. The flux requirement is 0, right? As per the mathematics as well, if you'll see, the flux is 0 at that time, right? And in physical sense, if you'll see, the flux is also 0 there at that time. So that means there is no problem there. So if I'm turning on at this moment, there is no problem of transient conditions. But if we turn on, let's say at this moment, this is let's say T1, let's say I'm turning on at T, so at time T2, let's say this is T2 and this is T1, okay, this is T2. So at time T2, if we are switching on, that means at time T2 we are switching on this SW switch. So at that moment there won't be any problem. So no problem. But think what will happen if you turn it on at time T1. So at time T1 the flux is 0. That means theta here is 0. But the requirement says that at that time the flux should be minus of phi m max. Let's say this is the maximum value, phi max or phi m. We used to say phi m, right? So I'm saying this is phi m, so this would be minus phi m. But in physical sense, since we are energizing at that time only, and let's say initially there was no flux in the core, the transformer is being used for the very first time. So obviously at that time there is no flux there. So the flux will start building up from 0, right? So the flux will start building up from 0, such that it will immediately try to reach to the value of, let's say at this moment the flux should be the maximum one, right? Because here demand says that at this moment, let's say if theta is at 180 degree, the flux should be 2 phi m, right? So actually if I draw it, it would be somewhat like this. and initially for some few cycles this would be in this direction only. So here if you'll see, the flux, the maximum flux has gone twice of the phi m. Okay, and this is the transient flux, not the steady state. This is the transient flux. Okay, so in the transient condition, for initial few cycles the flux goes to 2 phi m, up to 2 phi m. Okay, that is known as the doubling effect. So it causes doubling effect. Doubling effect. So doubling effect means the transient flux in the transformer or in the core of the transformer has reached to its double of its steady state value. Now what is the problem of this kind of condition? That means if you see the BH characteristic, you said this is the BH characteristic, and generally we operate at its knee point where this is phi m, right? But you have applied full voltage and you said that no, the flux demand has gone up to 2 phi m. Okay, so obviously for 2 phi m it will try to draw the even larger amount of the magnetizing current. Okay, so you can see here, this I have waveform I have taken from Chapman's book. So initially the magnetizing current will go, in the range of, I would say, like 100 times the rated magnetizing current. It is as good as the transformer has shorted at that time, but that is the momentary level. That is known as transient. That causes switching transient in the entire power system network as well. So the machines and even the other devices in the power system network, it should be capable of handling this much amount of current. Obviously it is momentarily, right? For a person, if you load it, so 100 times the rate of the magnetizing current. So you see the normal range is this much, right here. This is the normal range here. See here, marked here. Up to this range is the normal range, and normal range for the magnetizing current. And this is the rated current. But initially, if you see the magnetizing current, that is this much. So he was around 100 times of the, I would say, the normal. But it can go up to that range as well, around 100 times of the normal values. Okay. And after subsequent some cycles of this fundamental frequency, this transient condition will die out, and then we would be having a steady state conditions as well, where the flux would be phi m. Okay, so till now we have discussed about the entire working principle of the transformer, where we have talked about the ideal conditions of the transformer, then we removed the conditions on ideal transformers, and then we talked about the practical transformers and its equivalent circuit. And then we have seen like how to calculate or how to find the equivalent circuit parameters of the transformer by using open circuit test and short circuit test. And then we have seen even the efficiency and voltage regulation. Obviously those calculations were done for a single phase transformers, and they are equally valid for a 3-phase transformers as well. Okay, so if a transformer, 3-phase transformer, it is a balanced transformer, then you can easily draw the per phase equivalent circuit diagram of a 3-phase transformer, right? If the transformer is balanced, the load is balanced, the supply voltage is balanced, then you can simply analyze in terms of per phase voltages and current, and then you can scale it up to all the 3 phases, right? So all those analysis is equally valid for 3-phase transformers as well. Okay, so this completes the entire topic on transformers. And we have also talked about auto transformers, voltage and then parallel operation of the transformers. Okay, and then three-phase transformers, various connections of it, Scott connections, and then special connections like zigzag connections. So all we have talked about, and we have discussed about it. And then we have talked about one important aspect, which is the harmonic problem in a three-phase transformers, basically star-star connected transformers. And to mitigate it, we can use either tertiary transformers or tertiary winding, or we can use a neutral. The neutral of that start point should be grounded. And then we have talked about the switching transients as well. Okay, and next we will start about the DC machines. First we'll talk about the basic principles in the DC machines, and then we'll talk about the DC machines then. Okay, so we will stop here. Thank you.